All right, so I'm here a little bit early, maybe by 2 minutes or so. Um, but since I'm here, I can start to answer questions before the lecture starts. So if there are any questions, go ahead. I also want to tell everybody that I have a day-specific text channel for each days of lecture. So this way I can pin the URL to the YouTube recording. And all
I
right,
have
yeah,
one question.
yeah.
When is the next test plan for?
I do not know yet. There was a question in the general text channel about that. So typically, I do it in week 11 to week 12 or so.
Okay.
We are in week 9, I believe.
Okay.
So we still have about a week or so yet before we have to start to talk about it.
All
Um,
right.
yeah, the method of the test is going to be the interesting part is, how do we do the test, online. Um,
Yeah.
so one thing I think I will know for sure that I'll do is the test is going to happen at exactly the usual time that we have our lecture. So it's going to be
Hmm.
from noon to 1:20. So it's not going to be an online test where it's open for a few days or something like that. It's going to be exactly the same 80 minutes that we have scheduled for this
Okay.
class, because I don't think people have any reason that they cannot make it, because this is the time that we usually meet face to face.
Yeah. Yeah. Yeah.
Yeah. So the
I just
only
had a.
Yeah, go ahead.
Oh God. I was gonna say I just had an engineering test,
Uh
and
huh.
what we did was obviously we use Discord, we use Zoom there, but either way, we all had to log in
Uh
at
huh.
least with voice, whether or not our mic worked, just so our names were showing that we're in there, and
Mhm.
then we were emailed the documents,
Mhm.
and then we printed them, and then used our phone to PDF scan them back to her.
Yeah, we talked about this a little bit in a previous class, and some people commented on how it is more difficult to write the equations, if this is an online test, because I can potentially put everything onto Canvas,
Mm.
so that you guys don't need, so if as long as you can get onto the internet and use Canvas, you'll still be able to take the test. So I haven't really quite decided yet on the format of the next test.
Okay.
Yeah. All right. So we only got about. Let me check. Oh, it's noontime. It took me a few seconds to check the time, and and by the time I checked, it's already past noon. So I'm going to start the lecture today. Um, and on the live stream, you should probably be looking at the Discord live stream and not the YouTube live stream. The YouTube live stream is more or less just for recording purposes, and then the Discord live stream is for interaction, because I think the lag time is significantly less in the case of Discord, for a good reason, because Discord is not recording anything, and as a result, it doesn't need to keep maintain a buffer for encoding purposes. All right. So what we'll do today is I am going to finish up chapter 7, section 7 of the counting module. And so are there any questions from last time? Did any one of you got a chance to look at the content from last time? Or Okay. All silence here. Okay. So basically, UI of x here. Okay. So let me just kind of highlight the notation. So UI of x is the combination outcome set of an experiment that starts with x as a set of choices, and I over here is indicating how many trials do we have in that particular experiment. So you can see how this is defined recursively, because ultimately it depends on ui minus 1 of x minus e, or e in braces. What that is saying is we are taking every element of x in order to evaluate this expression here. Now, what this expression really is it looks really gigantic, it looks really complex, but once we figure out, what the set S really is, then it's not going to be that complicated. So what we do is we focus on what is ui minus 1 of x minus e in braces. What does that mean? Okay, because we have to understand the meaning and not really just look at the symbols and try to memorize the symbols. That will never work in this class. So when we look at these symbols, we have to ask, okay, what exactly is that? Okay, so U, once again, uppercase U is a set of combination outcomes. A combination is basically a set, okay, because the order is not important amongst the items within a combination. So ui minus 1 is an outcome, is a set of outcome sets. Okay, so this is from the get-go, this is a set of multiple sets. Okay, um, then what is a set of? Okay, each set in the highlighted portion of what you're seeing on the screen is representing the possible outcome of an experiment. All right, so what about that experiment? That experiment has I minus 1 trials. Okay, that's what the I minus 1 is doing as a suffix. Okay, and we need one more piece of information to generate, this particular set of sets, which is what items do we get to choose from, as the first experiment of this sub experiment, and that is x minus e in parentheses. Okay, why do we want to subtract e in braces? Well, that's because e is already chosen over here as the as the outcome of the first trial relative to this bigger experiment. So when I look at a smaller experiment, a sub-experiment, E is no longer available to me in this consideration because E is chosen as the first as the choice of the first trial of the bigger experiment. So that's why we choose this one over here. So this entire thing is really the set of all the possible outcomes when we start with this set of items and we have ni minus 1 trials. Okay, so we look at this entire thing, which is a set of sets. Each element of this entire set is by itself a set. Okay, so that is what uppercase S is representing. Okay, so uppercase S is really just representing one of the possible combination outcomes of an experiment that has I minus 1 trials, and the choices that we have is x minus e in braces. Okay, so what do we do with this S? All we do with this S is we make a union between that set and the set with just e by itself. Where is the e coming from? This e is what the outer or the bigger experiment has chosen as its as the outcome of its first trial. So when you combine these two, then we are basically just combining, okay, the first outcome is choosing this E, and then the sub-experiment can have many, many different combinations, but for this consideration, we only want to consider uppercase S. Okay, so this is the expression that is generated for each iteration of this particular loop here. So we are looping through every single combination that can be an outcome of a sub-experiment that has n minus 1 trials, starting with x minus e in braces as my initial choices. So when you look at this entire thing, all that is now representing is if I, as the outer experiment with I trials, if I choose E in X as the outcome of my first trial, then I can have this as a set of sets, okay, as possible outcomes. Okay, so when you go through every single possible E in X, then the union of all of that becomes all the possible combination outcomes when we start with X as a set of choices and have exactly I trials. So that's basically how this thing works out. So are there any questions about this? Okay, now remember, if you do have questions, go to the text channel that has today's date on it. So this way, it's easier for people to look up our interaction during the lecture. And I am not seeing any questions. All right. Okay,
I
so
do have a question.
yes, go ahead.
This will produce all of the possible results without replacement, not just
Without
a single experiment's worth of results without replacement.
This will generate all the possible outcomes and with the assumption that you do not replace something that you have chosen out of the set. So you cannot have repeating items as outcomes of trials. It's just like in Lotto. Okay, consider Lotto. Lotto is a very good example of of an experiment that is without replacement, and we only care about the combination. Is that okay or not?
I Yeah, well, I mean, yeah, I get it because as soon as you pull a number out from the lotto, you can't get that same number again.
Correct. And the order is not important either. So when they draw the numbers in a lotto game, they can draw the numbers as 5 4 3 2 1. Okay, they can draw the numbers as 1 2 3 4 5, or they can draw the numbers 1 3 5 4 2, or any one of those five factorial ways of arranging exactly those 5 digits. But it really does not matter in which order those numbers were drawn out of the basket. The ticket itself is order independent. Does that make sense?
Yeah, and this
Yeah.
formula follows that same deal where it doesn't matter what order these tuples are in.
There are no tuples. There are no tuples here because the only notation that we have here are set notations, and the only operations that we have here are unions. So there are no tuples, there are no Cartesian products here. So there's no such thing as ordering. Ordering is insignificant in all of these, in the entire expression that I have here.
Okay, I got it now. Thank you.
Yeah, as compared to the other one, which has a Cartesian product, and Cartesian product generates tuples, and tuples are order dependent. And as a result, omega I will give you a set of tuples, whereas u of I will give you a set of sets. So are we good?
Yeah, I got it now. Thank you.
All right, you're welcome. Any other questions? All right. So Nick, is your stream back up again?
Yeah, I don't know what happened. It cut off for some reason.
Okay. Yeah, it happened once to me. You guys all remember that, that one time when Discord kind of stopped working, toward the end of the lecture. Yeah, so I don't know exactly why it happens. I think it's probably some kind of timeout. Probably has to do with either internet connection, the speed of the connection, or the server itself, may be overwhelmed and it times out. I do not know exactly why it cuts out. Okay, so section 8, which is the last section of this module, is what is the significance of all of these counting stuff? It is significant because the counting, or what we are counting, is the denominator of discrete probabilities. In other words, I'm now connecting counting to the calculation of probabilities. Okay, counting is like, we look at a particular lotto game and then we ask how many different lotto tickets can be generated based on the rules of this particular game. That's counting. Okay, the next question is, what are my chances of winning? That is a probability. So you can see how these two are closely related, because let's say you want to win the jackpot of a lotto. Okay, so that means only one of the many different ways of generating the tickets is going to be the winning ticket for the jackpot. So in that case, it is 1 over the total number of possible tickets. That is, quote unquote, your chance of winning the lotto, the jackpot of that particular lotto game. So that is the connection between what we are talking about right now, which is focusing on counting, to what we'll be talking about next, which is probability. Are there any questions about how these two concepts are connected? even though I haven't really gotten started with probability yet, but do you guys start to see the connection between counting and the calculation of probability? Okay, I'm not seeing anything here. All right. So assuming there are no questions here, we're gonna move on. Okay. So this is back to Canvas, and we are just gonna move down the list of links within Canvas. We are just done with counting. The next one is a homework assignment. I'm gonna change the homework assignment a little bit. So this it's going to be an omega generator this time. So just kind of wait for me to change the homework assignment before you get on it. So the next thing we want to talk about is discrete probability, which is exactly connecting to the end of the lecture at this point. So when we talk about discrete probability, we are going to review some terms that we already know, and then we're going to introduce some terms that we have not yet introduced. So the terms that we have introduced is the term of outcomes, okay? And we also know what an experiment is, and we also know what a trial is within an experiment. So all of those terms we already know. In terms of all the possible outcomes, generally speaking, we call it an omega, even though in the previous module we use uppercase U to represent the combination outcomes, and we only use omega to refer to the permutation outcomes. But in general, within this new module, module 0308, we're going to use uppercase omega to represent all the possible outcomes. Okay, so sometimes it is a set of combinations, and other times it is a set of permutations. Okay. An event, on the other hand, is a subset of omega. So that's basically the definition of an event. It really is just a subset of omega. So now, what is the qualification of this particular subset other than everything in an event as a set has to be also be in omega? What else are we going to be talking about? It all depends on the problem that you're trying to solve. Okay, so there's no fixed rule to relate an event to omega. Okay, so for instance, okay, so we'll focus on this one here. In a Powerball lottery, a particular event may include all the tickets that win a particular prize. So let's go back to take a look at Lotto. And particularly, we want to look at the Powerball Lotto game. And the current outcome or the current winning numbers are 2, 23, 40, 59, 69, and then the Powerball number is 13. Okay, so that's the winning number of this round's Powerball. But what we want to do is to look at all the different ways of winning or getting something out of a Powerball lotto ticket. So what we want to do is to take a look at how to play, and let's see, maybe it's not specified here. Okay, the prices are not specified here. Game odds actually will show you some of the different ways of winning and also the odds. So as you can see here, the way to win a Powerball lottery is to have 5 of the 5 first numbers matching and also the Powerball matching. That is called the jackpot, and the chances of winning that is 1 in 292 million and something. But there are other ways to get something out of it too. And I believe the prices of all of the other ways of winning is also specified somewhere. And let's see, is it in how to play? Nope. FAQs. I'm just trying to figure out, what do you get, if you're not winning the jackpot but one of the other prizes. Hmm. Well, it has to be somewhere. I remember seeing that somewhere at some point. Because I believe the other prices are fixed amounts. Okay, maybe it's here. Yep, okay. So it's under last draw details. So what these numbers are indicating is if you only have the Powerball number matching, then you can get $3 out of your Lotto ticket. If you have one of the five winning numbers combined with the Powerball also matching, then you get $4 out of your ticket. If you get two out of five lucky numbers matching, and the Powerball also matching, then you get $8 out of your ticket. If you have three numbers out of the winning numbers matching, but the Powerball is not matching, then you get $8 in terms of your winning money. Okay? All right, so let's just stop here because I want to look at, okay, um, so how many tickets out of all the possible tickets is going to have the Powerball matching? Okay, and then we can use that to calculate the probability of if I just buy a ticket, what are the chances that I will get $3 out of it? Okay, so let's go ahead and do some calculations here, and I'll put the calculations within a notepad. Okay, this is from yesterday's lecture, and now we can reuse it over here. So to understand this question, it means we don't really care a single thing about the five winning numbers. We only care about the Powerball in this case. Okay. Now later on we'll find out that we actually do care because when we are trying to figure out the number of tickets, we actually have to figure that out. We have to factor that in as well. So the other thing we have to learn here is um, how many numbers can we choose from for the Powerball. So in how to play, it specifies that the Powerball, the power number, can be from 1 to 26. Okay, so we'll go ahead and do some calculations on this side. So the easiest way to look at this is to say, oh, so there's a chance of 1 over 26. It's highlighting because it's saving to a C file. So I'm going to save it to a text file so it doesn't have that highlight. There we go. Okay, so we have 1 in 26, but 1 in 26 itself is kind of a chance already. But it is not using the total number of tickets as a denominator. So the question is, how many tickets is going to match just the Powerball number? So that gets a little bit more complicated, okay? Because this one here is the Powerball, outcomes. Okay, there's only one Powerball outcome that is going to match the actual Powerball for a particular Lotto game. But then we have to multiply this to, oh, we have to look at all the other five numbers. Okay, what about those other five numbers? They all have to be, guess what? Non-matching, right? Because if we do match one of the other numbers, we are not going to win just $3. We're going to win a little bit more. Okay, let me switch back to that slide over here. If at least one of the other five numbers is matching, then you'll be winning, these prizes instead of the $3 one. And I just want to look at the $3 one. Okay, so what do we need to do? So now we need to look at the total number of combinations, but this time it is a little bit harder to figure out, what do we want to choose from and where we are choosing it from. Okay, so we still have to choose five things out of this set here, but they all have to be losing numbers because none of these can be a part of the winning number. So now the question is, how many numbers out of the 69 are non-winning numbers, because we don't want a single winning number. So the answer is, well, it's 69 minus 5, because this 5 is representing the number of winning numbers. So 69 minus 9 is representing the number of non-winning numbers. So out of those 64 non-winning numbers, we have to choose 5 of those. And this entire thing is telling us how many ways can we choose 5 out of the 64 non-winning numbers. So when you look at this entire thing, now it is the number of ways or the number of tickets or the number of unique tickets that will only win the $3 prize. Do we have any questions about this? I'm going to pause a little bit, let you guys kind of soak in and see if you guys have any questions. Yeah, go ahead.
I have a question. So calculating the number of people that will win just the Powerball?
Yes. So
Okay.
this is the total number of tickets that will win just the Powerball, or you get $3 back from your Lotto ticket.
Oh, the 35,000?
Out of the 292 million. Is that okay?
No.
No?
No.
Okay, Nick, your mic is kind of cutting in and out.
Sorry, is that better?
Yeah.
Okay. So you said we're calculating just the the number of tickets that will win off just the Powerball number alone, right?
How's that?
Yeah, okay. That makes sense. Can you explain the numbers again?
Okay. So the one at the beginning, this part here, is referring to how many ways can we choose the Powerball number so that it is the actual Powerball number. Well, out of
Okay,
26, there's only one, right? So
yeah.
therefore we have the one. Now, once we have fixed that, now we have to work with the other 5 numbers on the Lotto ticket. So we have to make sure that all of those are non-winning numbers, because if we had a single, at least one winning number, we'd be looking at these other prizes, not the one that only paid us back $3. Is that okay?
Yes, that
Yeah,
makes sense. So we're making the one is saying like, okay, they got the Powerball number,
correct.
and
Now,
then multiple. Okay.
yeah, so now we can also seemingly redundantly do this, okay? We can also say, well, what about the winning numbers, okay? How many ways can we choose a winning number in this case? So you guys might say, but we don't need a single winning number, okay? But there's still a count associated to it, because now we are choosing 5 minus 5, okay, out of 5, okay? So you go like, what exactly is that? It has got three fives in it. Which 5 is meaning what? Okay, so let me explain it. This 5 refers to the 5 winning numbers. Okay, this 5 is referring to how many of those winning numbers do we want to discount. Okay, we do not want this number of winning numbers. So in this case, because we want 5 non-winning numbers, so that means out of the 5 original winning numbers, we want none of them. And then we ask, oh, actually I keep flipping the order, excuse me, it should be like this. Okay, so this makes more sense now. This one is saying out of the 5 winning numbers, okay, how many ways can we choose none of them? So what do you think? I'm telling you the winning numbers are 1, 2, 3, 4, and 5. Okay, how many ways can I choose none of them?
21.
No, just one. An empty set. Okay, let me present this as an example like this. Okay, so this 1, 2, 3, 4, 5. How many ways can I choose none of these as elements in a new set? And the new set can only be a subset of the set 1, 2, 3, 4, 5. So as a subset of the set 1, 2, 3, 4, 5, how many ways can I make this subset so that it contains none of the elements of 1, 2, 3, 4, 5?
For your example, you would just choose none of them.
Yep.
But for the lottery, you still have to choose numbers, don't you? I don't think you
Yes.
can play
Yes.
without anything
Yes.
but the
But
Powerball number.
but that's coming from here. That's coming from this part here. So what you need to do is to look at, okay, so when you look at a lotto ticket, look at it as, look at it as, let me reformulate this because this is the first time I introduce this particular way of looking at a lotto ticket. Okay, I got it. Okay, so look at it as something like this. Okay, so each lotto ticket, and to be more specific, each Powerball lotto ticket can be seen as something like this. Okay, so I'm going to use this parenthesis here only to emphasize that we are performing this operation first. So this one has nothing to do with a tuple. Okay, so we are looking at the set of all the winning numbers. Okay, union with the set of the non-winning number of that particular ticket. Okay, and then now we have a tuple because it has to be tupled with the Powerball number. Okay. All right. So now I will go ahead and explain what each letter means. Okay. W is a set of winning numbers on a ticket. N is a set of non-winning numbers on a ticket. And then P is the Powerball number. Okay. All right. So we look at this and go like, okay, what does that mean? Okay, so I'll give you an example. So the way I'm going to give you an example is to utilize what is actually happening in this particular draw. It's right here. Okay, so we'll go ahead and copy that. Okay, so let's say winning numbers are 2, 23, 40, 50, 59, and okay, let me move this one over here, and 69, and the Powerball number is 13. Okay, so give me a ticket. Okay, a ticket that wins $3 would look like this. Okay, so what is that going to look like? If I want a single ticket, so can someone give me an example of a single ticket that will only win me $3? Because
1, 22, 39, 58, 68, and 13.
yep, exactly. So let me do that one more time. Okay, but the W set is going to be an empty set because we don't want any winning numbers in W, right? So once again, can you repeat what you have chosen for the non-winning numbers?
1, 22, 39, 58, 68, and then the Powerball is going to be 13.
Okay, and the Powerball number is 13. That's right. So when I format a ticket in this particular way, so this ticket can now be seen as the winning number as a set, which is an empty set, union with the non-winning numbers, which in this case, for this particular ticket is 1, 22, 39, 58, and 68. And then the whole thing, because this makes a set, but I want to take this set and make a tuple out of it because the order is important between the set and also the Powerball number. So this ticket is now represented in this particular fashion. Is that okay? Does everybody understand why I'm representing a ticket in a very weird way? Because I'm separating the winning numbers of that ticket from the non-winning numbers, and I'm clearly indicating the Powerball number has nothing to do with the winning numbers or the non-winning numbers. Is that format okay?
Yeah, the way this is visualized makes it much easier to understand. Thank you.
Okay, absolutely, yeah. So this ticket wins $3. Okay, so now the question is, how do I generate all the tickets that will also make $3? Okay, so now the question is, how do we generate all tickets that win $3? That is the question. Okay, so we look at the format over here. Okay, and we ask, how many ways can we generate an empty set out of the winning numbers, because the winning numbers in this case are these particular numbers. So how many ways can we choose out of these five? Choose none of these five. That's only one way. Okay, that's only one way to choose nothing out of five. In other words, if you consider C50, that is actually 1. Now, does that make sense? Okay, so let's see whether this makes sense from two different perspectives. Oh, you guys cannot see what I'm typing. So let's see whether we can make sense out of why the number of combinations of choosing none out of 5 is exactly 1. Okay, there are two ways to look at this. The first way is to say how many subsets can I make out of choosing you know any number of these 5 numbers, so that there's nothing in it. There's nothing in the new set. There's only one way, because there's only one empty set that meets that requirement. So as a result, the number is 1. Okay, so that's the first way to look at it. The second way to look at it is not going for the semantics or the meaning of the words. The second way is to look at the actual definition of what is combination. So hopefully you still remember the combination of choosing m out of n is n factorial divided by n minus 1 factorial times m factorial itself. Okay, that is the definition of the number of combinations. So in the first case, when we plug in these numbers, what do we get? We get 5 factorial divided by 5 minus 0, the whole thing factorial, and then we also have 0 factorial, because m in this case is 0. So we got 5 factorial divided by, okay, in this case, 5 minus 0, the whole thing factorial, is really just 5 factorial. So the mystery here is, what is 0 factorial? Well, as it turns out, 0 factorial is by definition 1. So that means we have 5 factorial divided by 5 factorial itself, which is also just 1. So is that working? Does everybody see, how we can look at combination, or the number of combinations, and still come to the same conclusion of, choosing none out of 5? There's only one way to do it. Are we good so far or not?
Yeah, so in this case, we're not looking at all 20 numbers. We're considering the ticket that has winning.
Correct. Yep.
Okay.
Yep. All right. So if this one is working out, let's move our ambition up a little bit and say, okay, let's go back to this slide here. And let's say that, we just want to afford a Starbucks coffee, and we want to target, matching only 3 of the matching numbers, none of the Powerball, and just, exactly 3 matching numbers. Okay, what would a ticket look like in our case? Okay, so we go back to our example here. So we look at the ticket in this kind of weird format, and this time we have to choose 3 out of the 5 winning numbers. Okay, so I'm gonna choose 240, 59, and those are the 3 matching numbers. Okay, and now we have to union this with 2 non-winning numbers. Okay, and there are so many non-winning numbers, it's pretty easy to find 2 of those, like 5 and 6 are both non-winning numbers. So these are the 5 numbers, whether winning or not, or matching or not. These are the 5 numbers for the first part of the Powerball ticket. But we also have to make sure that the Powerball number is not matching. Okay. Now, since the Powerball number for this particular case is 13, we can choose 2. Okay. And now this is now representing a ticket that only has exactly 3 numbers matching the winning numbers, and nothing else. And it's worth $8. So are we good so far? Does everybody understand how I am representing a particular specific ticket that is only going to earn me or win me $8? Are we good so far?
Repeating that last step again, please.
The last step. You mean the
So
2?
that, yeah, how you got that equation?
it's not exactly equation. It is just a way to express a ticket. This part here is taking the part of the set W, which is representing the number of numbers on your ticket that actually is matching is a matching number. Are we good so far?
Yeah.
We see that 2, 40, and 59 are all matching the winning numbers. But we also need two numbers that are not matching. So 5 and 6 are not matching, so they are not one of the winning numbers because you need to pick 5 numbers. Okay, if I need specifically only 3 of those 5 numbers to be a winning number, that means the other 2 has to be non-winning. Is that okay? So I choose 5 and 6 in this particular case.
Yeah.
Okay. So the 2 over here is really just representing the Powerball number on my ticket. The Powerball number on my ticket is 2, but the actual game says it is a 13, so it is not matching. That is also a necessary condition because remember, we want to only make $8 by matching only 3 of the numbers. So
Thank you.
is that okay? All right. Okay. So now that we understand how this format works, now we have to do some counting. In other words, we look at this part here and go like, how many ways can we do this? Okay. How many ways can we do this? How many ways can we do this? And how many ways can we do this? That ultimately is going to answer the question, okay? Because we just multiply all of those numbers together. That would give me the total number of tickets out there, okay? Total number of unique tickets out there that will only get whoever owns the ticket $8 by matching 3 numbers. I know there's another way to win $8, but this is the one that I'm focusing on. So are we still good with this discussion where I'm heading? Sort of? Maybe?
Still good. Yeah.
Still good? Okay, very good. All right, so now we only look at this part here and say, well, how many ways can I make a subset out of a set of all the matching numbers? This is the set of all the matching numbers. It's a set of 5 things, and I need a subset that has exactly 3 items in it. So instead of giving me a number, can someone give me an expression that we have already introduced that will give me exactly that number? It starts with A. The same letter that combination starts with.
C.
Yep, exactly. It starts with a C, even though it sounds like a K, but it's a C. So it's a C, and how many things can I choose from in this case? What are these things? I'm choosing from what set? How many items is in that set?
3.
3 is in here, okay? We're choosing 3 items out of how many?
5.
Sorry?
Wouldn't it be out of 5?
Yes, it is out of 5. Very good. Okay. So that's how we calculate this one is we're choosing 3 out of 5 because the 3 is representing the number of winning matching numbers and the 5 is representing the total number of numbers on the winning lotto ticket. Is that okay? So this 5 is basically the cardinality of the set of all the matching numbers. Okay, let me re-highlight this. It's the cardinality of all the matching numbers. So what about this part over here? Okay, so let me move over to here. How many ways can I choose 2 non-matching numbers? Okay, so once again, the order is not important, which means we do not use P, which is permutation. Once again, we use C as a combination. But this time, what is the cardinality of the set of all the non-matching numbers? How big is that set?
2.
No. Out of
Maybe
that set, we
5.
have to choose 2. But how many numbers are non-matching out of the 69?
Should be 69 minus 5, right?
Yes.
64.
64, that's right. Okay, so we got 64, and out of those 64, how many are we choosing? That one is kind of visual.
5.
2.
2, that's right.
Oh, I
Okay.
mean 2. Sorry.
All right. Okay, so we got one more thing over here, okay, because we have to make sure that the Powerball number is not matching. There are 26 numbers to choose from, for the Powerball number, and I have to make sure that I miss the actual correct Powerball number. So how many choices do we have here?
So we're
25.
choosing 1 out of 25.
So it is 25. Okay, there are 25 different ways to choose that not matching Powerball number. Is that correct? Are we good?
Yes.
All right. So now that we have figured out how many ways we can make this particular subset, how many ways we can make this particular subset, and how many ways we can make, select this number, what is the total number of unique tickets then? Well, you just have to multiply everything together. So if you multiply everything like this, whatever the answer is, would be the total number of unique tickets that only matches 3 out of the 5 winning numbers and it does not match the Powerball number. Are we good with this?
I do have a question, Professor.
Yes, go ahead.
Would having an empty set still be valid for any one of those chooses or combinations?
Yes. So in the first one, okay, we want an empty set over here because we only want to match the Powerball number, which means the set of all the winning numbers is empty. So if you look at this particular format to win exactly $3, okay, so once again, we look at the numbers of each thing, okay, just like with the second one. And I'm going to put one more pound here because each pound is representing, a number on the ticket. So now, for the first one, we are now looking at out of the 5 numbers, okay, out of these 5 numbers over here, we want none of them, okay, because it's an empty set, so we're choosing none of those. Out of the not winning numbers, and we have 64 of those, okay, out of those 64, we want to choose exactly 5 because we want all 5 numbers, the first 5 numbers on the ticket, they're all missing the winning numbers, okay? And then we look at the Powerball number. Well, we do want to match the Powerball number, and there's only 1 out of 26 that is matching. So when we multiply all of these together, that will become the total number of unique Lotto tickets out there that will give you $3 because it doesn't match any one of the 5 numbers, but it does match the Powerball number.
But that's the only situation, unless we didn't win anything.
No, it is not the only situation. Okay, so we'll get to the other situation later. Okay? Okay, first thing first, okay? I just made a whole bunch of claims without actually validating or at least verifying that my claim is correct. So now what we need to do is to calculate, are we really sure this is boiling down to the number that we want to look at? So when you put this into a spreadsheet, you use combin to mean combination. So we have that times the combin of 64.5 and then times the extra 1 which is here. I know times 1 doesn't looks like it is important, but it is important to keep a place for this number because in general it can be a non-1 in some cases, so that's why I'm keeping that place. Okay, so now we can just go ahead and copy this and paste it into any spreadsheet. If you want to use Google Sheet, that works. If you want to use Excel, that works. Or if you want to use, okay, let me look at my office here. I got LibreOffice Calc, that will work as well. Okay, so we'll just go ahead and paste that equation in. And the answer is 7624512. And then we go back to the website and look at the chances or game odds. It goes like, hey, Tech, none of these numbers is matching what you have. Well, that's because these are already odds of 1 in something. Okay, so what we need to do is to also divide that number by the total number of tickets out there. Okay, but instead of pasting that number in, I will actually do the entire calculation. Okay, so we'll Control C, copy this, and paste it over here. But this time we are looking at 5 ways to let's see, we are looking at, okay, this time we're looking at all the possible tickets. So when you look at all the possible tickets, there are 5 ways to okay, we need to choose 5 out of 69, okay, and then we have 26 of the Powerball number choices. So this is the denominator, this is the numerator, this is the denominator, and we want to find out what is the odd in. So that means we are dividing this number, the larger number, by the smaller number. That will give us the chance of 1 in. Okay, so we'll say what is the okay, this is odd in 1 in blah blah blah. Okay, so that is now this number divided by this number over here, and it's approximately 38. So when we go back to the website over here, it says 39. Okay, somebody has a rounding, consistency is not the same as mine, because in here it is 38.32. So normal rounding would round it down to 38, but I guess the state wants to round it up just so that people cannot claim the state is misleading people into believing that there's a higher chance to win that $3. That's just my speculation. Okay, so but this is not a really common way to define probability. Odds 1 in something. Most people, mathematicians and scientists, would look at probability in the opposite way, which is you start with what you want. Okay, you start with the event. Okay, this is the cardinality of the event. Okay, which is a subset of omega, of all the possible outcomes. And this one over here is the cardinality of omega itself. This is representing the number of items, that is in the possible outcome set. So when you look at that, okay, these two things are representing the same thing. If you take the reciprocal of one, you get the other one. Do we have any questions about these two numbers? You can see in the equation, in the formula, one is A2 divided by A1, and the other one is A1 divided by A2. So they're reciprocals of each other, except this is how they want to represent it in the Lotto website, which is the odds of winning as in 1 in 39, which basically boils down to, if you buy 38 or 39 tickets, you probably will get one that will get you that $3. That's basically what it's saying. So do we have any questions about the discussion up to this point? No questions? So no one is asking why the Lotto website does not use this number, or at least use a percentage. Like in this case, it's 2.6% instead of 39. So does anyone want to know why that is the case? Or
I'm guessing it's
It
so
looks
people
better.
will buy the tickets.
Exactly. Because if you only got a 2 point something percent to get $3 back, what do you think those numbers would look like in all of the other cases? Okay, let's not go too far. Okay, so what we'll do is we're going to go back to the notepad here. So we're going to finish this calculation. Okay, in this case, we want exactly 3 of the matching numbers and not having the Powerball number to match. Okay, so we'll go ahead and actually do this computation. So we look at the combination of choosing 3 out of 5 times the number of combinations of choosing 2 out of 64, and multiply it by the 25 numbers that do not match the Powerball number. Okay, so now we take this and plug it into the spreadsheet, and I can plug it maybe in here. There we go. And we want to do the same calculation. So if you want to express this, as an odds kind of representation, then we are looking at this number, which is the total number of unique tickets divided by the number of tickets that has exactly 3 matching numbers and the Powerball number does not match. So that chance is about 580 to 1. And if you go to the website, I believe it is the same thing. Okay, they say it's 580. So what that is representing to a person who does not really have a whole lot of understanding of probability is, if you buy 580 Lotto tickets, one out of those 580 tickets will get you this price of $8. Okay? But what if you are a mathematician, a computer scientist, or a statistician or a scientist, and you want to look at this as a probability, which is the better way, I think, is a better way to represent these things. Then you're dividing the cardinality of the event, which is a subset that we are interested in, by the cardinality of omega, which is the set of all the possible outcomes, and the chances boil down to 0.17%, which is a pretty low number. Okay, if you ask me, that's a pretty low number. Okay, and I think the reason why things are expressed in the odds of 1 in something is twofolded. One is if it is expressed in probability, most people will look at that number and go like, wow, that is really small, I'm not going to play this game. And the second one is most people understand 1 in, as a way to express probability. But when you express something using decimal points, and percentages and whatnot, that may not be something that is commonly understood. Is that working out okay? Are we still good so far?
Yeah.
Okay. So using this method and using this table, or not this table, the other one. Okay, let me go back to the table that we are talking about, this one here. So using both of these tables, except for the jackpot, I think the second prize, the second highest prize of Lotto is a fixed number. I don't think this number floats, with the jackpot. So we can actually figure out, okay, if I spend, is a Lotto ticket still $1 now?
I think it's 2.
Is 2? Okay, so if I spend $2 to buy a Lotto ticket, what is the potential return of those $2? We can actually totally calculate that amount. Okay, so on the average, okay, out of $2, what am I going to get back based on all of these prize monies? Are we good so far? I mean, are we still doing okay in terms of figuring out when to use combination and how to use different combinations in this case? Because we have let me go back to the notepad here. Because we have two combinations in place. One combination has to do with the numbers that are matching the winning numbers, and one combination is here to deal with the numbers on a ticket that do not match the winning numbers. So that's why we have two different combinations. So is that part okay?
Yeah, and the reason we're using combinations is because we're considering, like, if it's 2 40 59, we're considering it the same as 42 59.
That is correct.
Okay, cool.
Because order is not important in this case. All right. So, okay, here is something that is a little bit out of the scope of this class. But the question is, when is a good time to buy a Lotto ticket? In other words, when you combine the chances of winning and the actual prize money, when do you think is a good time to buy a Lotto ticket? Okay. So to work this out, okay, I'm gonna work it out the same way as in this format. So in this case, the only ticket that would get you a jackpot is the set of all the winning numbers is exactly all the winning numbers, okay, which you cannot see anymore. So I'm just going to copy and paste all the winning numbers up here. Okay, so copy and paste that. Don't know why the cursor turns into a...
Professor,
Yeah.
real quick.
Yeah.
Can the Powerball number only be 1 or 25 in the equation?
It's from 1 to 26. So the numbers you can
26.
choose from for the Powerball number is from 1 to 26. But the count here is either 25 or 1, because 1 is representing we want it to
It's a
match,
number.
and then 25 is when representing when we do not want it to match.
All right.
So there
Yeah, that's what I was asking.
Okay, yeah, there are 25 ways for it not to match, and there's only one way for it to match.
Thank you.
Okay? Yep, you're welcome. So, and then 13 has to be here. Okay, so this is the jackpot winning ticket. Okay, there's only one ticket that can win a jackpot, and this is it. Okay, we're looking at it right here. So now the question is, how many tickets can do this? Okay. Now I know this is a really stupid question, but let's do it anyway. So we are looking at here and say out of the 5 numbers that are winning, okay, we want all 5 of those. So, okay, out of all the non-winning numbers, we want none of those. So there are 64 non-winning numbers, and I want none of those. And of the Powerball numbers, there are 26 possible choices, but only one is matching, so we want one of those. So now we look at the multiplication or the product of these 3 numbers. Okay, and I don't need a spreadsheet to figure this one out. Okay, and I'll tell you why that is the case. This is a very easy one to work out. All right. So the last times 1, obviously, you can simplify it out because anything times 1 is the original thing. Okay. The second one, what's like the second last item, which is how many ways can we choose nothing out of 64? We already answered that question earlier. It is an empty set, and there's only one empty set. So that's why, C64 0, C anything 0 is always just 1. Okay. What about this one over here? Okay. How many ways can we choose 5 things out of 5? That seems like a big number. Okay. But it's a big number only when we're using permutation. Because when you use permutation and you have 5 things, let's say 1, 2, 3, 4, 5, then you have 1, 2, 3, 4, 5, you have 1, 2, 3, 5, 4, then you have 1, 2, 5, 4, 3, 1, 2, 5, 3, 4, and so on. But guess what? All of those are really the same combination. So combin 5, 5 or combin n, n is always just 1. Okay, so now we have 1 times 1 times 1, which obviously is just 1. So there's only one ticket out of 290 something million that is going to get you the jackpot. Okay, so we'll put it into our equation here. Okay, so we say there's only one ticket, and what is the 1 in odds? Okay, that one is pretty easy because anything divided by 1 is the original thing. So if you want to look at this as the odds in 1 in, it's going to be 292 million something to 1. And if you want to look at the probability, which is actually more useful in our calculation, then it's the reciprocal of the other one, which is just 1 divided by 292 million something, and it gives you a pretty small number. Okay, so based on this pretty small number, or based on the 1 in probability, what is the jackpot that you need in order to say, yeah, I think it's worthwhile to buy a lotto ticket now? So what do you guys think? Oh, okay. Nobody wants to.
Well, it would
Yeah,
be
go
when
ahead.
there's the least amount of players, which typically is when the jackpot is the smallest.
Yes. Okay, so you just brought up a very good point. So let's consider that point a little bit later. Okay, so the first thing we want to do is really just to say that they're exactly. Okay, let me go back here. There are exactly 292 something million tickets. In other words, there are no duplicate tickets out there ever. Okay, the state would just print all of these tickets. When they're sold out, they are sold out. Okay, so in that particular case, the prize money has to be this amount times 2 because you spent $2 to buy that ticket, right?
Correct.
So that means the prize money, okay, has to be $2 or whatever the dollar amount is for each ticket times this, okay, in order for you to consider, okay, it's worthwhile for me to play this time. Okay, that's the first thing. But if the jackpot money, okay, now you have to multiply this with taxes. Okay, you have to factor in state and also federal tax. I think at this particular bracket, it's going to be at least 50%. Is that about right or not? I don't make that much money, so I
Probably.
wouldn't know. I don't make that much money, so I wouldn't know. So let's say it's 50% of taxes. So that means, in order
It also
to make it
depends on how you take the money, though.
right,
Like,
that
you
is
can get
correct.
taxed less if you take it like
I believe lump sum is something like 47%.
47. Okay, so we'll take the lump sum of 47% because people who win the jackpot may not plan to live too long. Yeah, go ahead and look up the longevity of people who win jackpots. It's not really that high.
No, it's not.
And there's a reason for that. Okay, so the jackpot has to be at least this much money, which is almost a billion, right? Yeah, so this is like 0.85 billion in order to consider. So, but if the jackpot is almost a billion, and the actual tickets, I mean the actual lotto system does allow duplicate tickets. In other words, they will keep cranking out those tickets at 7-Eleven, for anyone who wants to spend $2 to buy a ticket. So that means there'll be duplicate. Okay, so there'll be duplicate items, which typically means there would be duplicate or multiple winners, and they have to divide the prize money up, amongst all the people who has the jackpot, combination. Does that make sense? And that I have no model. Okay, I do not know how to model how many people will buy a lotto ticket or how many tickets each person will try to buy when based on the jackpot money. Uh, there are some studying about that. In other words, if you look up the last draw data, they do give you some statistics about Oh, this is really useful. Okay, so this is really useful. It's telling you that of all the tickets sold for this round of the Powerball Lotto, exactly 35,196 got $3. Okay, and exactly one of them got $27,591. So these are the exact count of winning tickets of this particular round of Lotto. So based on past history of this particular Lotto game, you can probably do a correlation between the prize amounts, okay, especially the jackpot amount, and the total number of people who played Lotto. And now these numbers are only reflecting people who win, but since we know the odds, so you can always use the odds combined with the actual number of winning tickets to extrapolate the actual total number of tickets sold. Is that making any sense or not?
But that's based on their data being accurate. There may be unrecorded cases that go through that.
Um, I do not think they're unrecorded tickets because I think these are not based on claimed tickets. I think these are based on printed tickets.
Well, that's what I was getting at is you may have a bunch of people who don't claim, so they don't.
No,
Well, maybe
no,
they do count. I don't know.
no. I don't think these are claimed tickets. I think these are the actual count of tickets issued, but not tickets that are claimed.
Oh, okay, I see what you're saying now.
Yeah. So when you combine this number, let me go back to the spreadsheet. Nope, not here, but here. So when you combine the number that I have highlighted here with the probability which is over here, then you can actually figure out how many people actually bought tickets or how many tickets were sold, or at least an approximation of that. Is that okay?
Right,
Does that
yeah, I see it.
actually give a good approximation? Because isn't it possible that like only 40,000 people bought and 35,000 won? Isn't that like possible?
It is possible, but it is unlikely. If you look at this number, then your estimate can be off by a whole lot, right? Because it's just one versus some really small number. But when you look at this number, which is pretty big, okay, it okay. So this kind of goes into another. There's another term in this for this in statistics. The bigger the sampling size, the closer you are to the true mean. Okay, so it works this way as well. So we'll go ahead and just calculate this part over here. So I'm gonna copy and paste this number into the spreadsheet. Okay, come on, select, copy, and paste it here. Okay. All right. So we got this number. And then we have this probability. So now you can divide this number by the probability to get to the total number of tickets sold. Okay, based on the distribution of this probability. Okay, so we'll go ahead and do the calculation. It will be the actual number of tickets for a particular prize divided by the probability of winning that particular prize. So in this particular round of the lotto, the according to this method, the estimate is about 1.3 million tickets were sold. Is that working or not? Yes, no, maybe.
Yeah,
Okay.
if we're using it like that.
Yep. And you can use the other one too. Okay, so we can use this one also. So this one is meaning exactly 3, okay, which has now a smaller number. So we can copy and paste this one too and use that to give us another estimate. So these two estimates should be at least in the same order of magnitude, right? So we say, what is this number, which is the actual number of tickets winning that particular prize, which is matching only 3 of the matching numbers, but not the Powerball number. So divided by the actual distribution. And you can see how both of these are giving us 1 point something million, and they're off a little bit. Okay, that is to be expected. Is that okay? So you can go back into the history of a lotto game. Okay, I'm pretty sure somewhere there's a statistics. Somebody keep track of all of these numbers in all prior weeks. So you can use that to model and basically say if the jackpot is this much, how many people are going to play? If the jackpot is this much, how many people are going to play? And combining that with this number over here, then you can determine, when is it statistically speaking really worthwhile to play the lotto game. And what do you think that answer is going to be?
It's not.
It's never worthwhile to play the lotto game, because if it is ever worthwhile to play the lotto game, then the state is going to lose money, which is not the purpose of the lotto game. Is that kind of making any sense? And that part does not require any statistics. It doesn't require CISP 440. All you have to think about is if you walk into a casino and it has got well maintained carpet, really nice lights, and employees who are professionally dressed and so on and so forth, then the first question is who is paying for that, right? And the only thing that is making money is really gambling. Okay, you might say oh, but there's the game arcade. Okay, well the game arcade is not going to use the video game arcade. It's not really going to make that much money, especially if I'm playing. Okay, because I can pay like a few quarters and really hang on to a game for a long time. um, the slot machines, do not really make as much money. I mean, it's a continuous stream of money, but not that much. But all that money to pay for the electrical bill, to pay for the rent and whatnot, has to come from somewhere. So that means, gambling in these establishments is guaranteed to lose in the long run, because otherwise the casinos cannot exist. So is that line of reasoning working or not? Okay,
Yeah.
no comments. So why do you think people are still going to the casino?
They still have a chance to win.
There's that rush of almost winning that keeps them
They're
hooked.
addicted.
Or they win. They
Hope.
spend money.
It's just hope.
Yeah, no,
It
they
is.
spend money. They lose a ton, but they win a small amount. Like I used to
Well-
work at a casino.
Oh.
and I had
Something I
like, there was
learned
guys
is
who would like spend like millions of dollars and then win like $200,000 and be happy about it, even though they lost
Okay.
hundreds.
well, some
of
people do
thousands.
actually profit off casinos. Like they don't. Some people actually don't have jobs. So like my aunt and are actually professional gamblers, and they profit. So you can play games where you play the players, not the house, such as like poker,
Mm-hmm.
as well as those arcade slot machines. There's actually people that walk around the casinos and choose which ones to play based on which ones are about to pay out, because they always pay out after like certain specific things. They're designed like that. They're not truly random. The
Okay.
arcade one. And so there's people that actually just walk around and play specific ones and
So
win.
some people have a specific way to win money in the casino, which means the other people who go to the casino is going to lose even more.
Yeah,
Does that make sense?
exactly.
So
Yeah.
those other people who do not come in with a technique, to basically say, okay, in the long run, I'm going to make some money because I got this technique. All of those people go in because of what I'm highlighting on the screen. They have a belief. Okay, it is a belief that is not based on numbers, it's not based on facts. It is really just saying that I think I'm luckier than the next person, and as a result I'm gonna make money. So yeah, so uh, I'm not gonna go too much into the addiction of gambling, but it is a serious thing. I mean, it's actually more serious than some substance dependency. All right, so I'm hoping this lecture up to this point is helping you guys to convince you guys, at least helping you to assess, the situation and go like, okay, what are the chances of winning a lottery game? Okay, um, are we still good so far? In terms of the notes. Okay, let me kind of go back to the notes here.
Yeah, so
Yeah, go
back to
ahead.
my original question of when you can have empty set, there's only three situations where you win, you only win the Powerball, you win everything,
Yes.
and when you don't win anything. Are those the only situations where you only have empty set then?
In this particular case, yes.
Okay,
Hmm.
okay, that's
Yep.
what I was curious about.
Yep. All right. So getting back to the notes, okay, I may not have enough time to go over this today. So I'll just go ahead and introduce the problem. I'll have you guys to think about it, and then on next Monday we can come back and actually look at this in more details to analyze the problem in more details. So the birthday problem is an interesting one. It is asking the question of X many people. Okay, so let's say the class now has 50 people. Okay, so the question is, what are the chances that at least two people in the class share the same birthday? Okay, so in this class, let's say we have 50 people. So the question is, of all the 50 people in this class, what are the chances that at least two have exactly the same birth date? Okay, um, the chances is actually higher than most people think. Okay, but what we are focusing here in this example is not so much the number itself, but how do we do this calculation? Okay, how do we compute this? Um, so I'm not gonna work on this, in details, and the numbers are actually calculated at the end here. So you can just kind of read through this and understand, how to set up the equations. And also, what I use here to set up the equations is only one way to do it. There are actually multiple ways to set up the same kind of equations. I'm only using one of those methods. Um, so this is, one of the examples. The other example has to do with coin tosses, and that one is with replacement. Now, coin tosses is also a very interesting question as far as computer science is concerned, because when you look at the transmission of a bit, okay, a binary digit, okay, which can either be a 0 or 1. So let's say you're transmitting over air, okay, we're talking about Wi-Fi communication here. Don't you think there's an interest in computing what are the chances that in the transmission there will be at least one bit that is received incorrectly? Okay, that seems like a legitimate question to ask, because the error ratio of transmission can limit the actual bandwidth. Because if a packet has one bit that is transmitted incorrectly, then the checksum will catch it, and then you have to retransmit that packet again, which means your actual throughput is going to reduce, right? So what does that have anything to do with tossing a coin? Okay, well, tossing a coin in this case is kind of like having a very loaded coin. Okay, so if you think about correctly transmitting a bit as tossing a coin, that coin is probably very loaded. In other words, the chances of a bit being transmitted correctly is pretty high. Okay, maybe 99.999%. Okay, But there's still that one little off chance that that bit may be transmitted incorrectly, okay, due to noise, due to some issues. There's always a chance. But now you have a problem that is just like a coin toss problem, okay? What are the probabilities that you have at least one bit transmitted incorrectly within a 4 kilobyte packet? What are the chances that you have 2 bits within a 4 kilobit packet that is transmitted incorrectly, and so on? So that is why coin toss is interesting in computer science, because we can use the math of probabilities of getting a particular specific outcome in a coin toss to model certain behaviors, especially in networking of computer science. So that's why section 4 or example 2 is also of particular interest to computer science people. So if I scroll forward a little bit more, section 4.1 is starting to get into some math here and is formatted incorrectly. There are supposed to be 2 parentheses around nk and also n and then k minus 1. I'm not really sure why it is not showing, because the PDF hopefully has it.
The PDF does. I printed it.
Okay, so the PDF does have those parentheses. It could be just a Firefox issue. If you open this in Chrome, that it may be different. But last time I checked Chrome, it is actually worse than Firefox. So I'm not really sure whether it will open up correctly. You know what? I think I know why. Because I was using the wrong browser. Okay, just give me a second. No, I shouldn't say the wrong browser, but I'm using the wrong setting of a browser. Okay, so let me go back to section 4.1, which is up, up, up. Okay, and I'm going to reopen this tab. I'm going to reopen this tab, but without using a container. I just got into the use of containers. Oh, okay, that doesn't help. Okay, so I'm going to look into this problem and try to find out why those parentheses are missing. So this pretty much ends today's lecture. Are there any other questions before I take a short break before coming back to my office hour? No questions? All right. So if there are no questions, I'm going to stop the YouTube stream